Did you know Albert Einstein, the genius behind the theory of relativity, was a bit of a rebel in his youth and even dropped out of high school? Yes, that's right. Our story begins in the late 19th century with a curious and headstrong young man named Albert. He didn't quite fit into the rigid structure of traditional education. Some even labeled him a troublemaker. But within this nonconformist mind, an insatiable curiosity was brewing. From a young age, Einstein was fascinated by the mysteries of the universe. He would spend hours lost in thought, contemplating complex concepts like space, time, and the nature of light. As he grew older, this fascination turned into a passionate pursuit of knowledge, leading him to the world of theoretical physics. From the alleys of Munich to the prestigious halls of Zurich Polytechnic, Einstein's journey was anything but ordinary. Despite his unconventional start, Einstein's genius would lead him to develop theories that forever changed how we understand the universe. Imagine you're on a train moving at the speed of light, and you flick on a flashlight. What happens? Now, you might think that the light from your flashlight would zoom ahead of the train since you're already moving at light speed. But that's not what happens according to Albert Einstein. Einstein proposed the idea that the speed of light is a constant and unchangeable fact of our universe. He suggested that light always travels at the same speed, around 186,000 miles per second, regardless of how fast you're moving when you turn on the light, or how fast the source of the light itself is moving. Let's go back to that train. You're on it, whizzing along at the speed of light, and you flick on your flashlight. According to Einstein, the beam of light from your flashlight doesn't shoot ahead at twice the speed of light. Nope, it just calmly carries on at its usual speed, while you and your train continue your light-speed journey. Einstein's idea might sound strange, but it's been tested and confirmed by countless experiments. It's a fundamental part of our understanding of physics and the universe. It tells us that light doesn't play by the same rules as other things in the universe. When you throw a ball from a moving car, the ball moves faster because of the car's speed. But light doesn't work that way. It always moves at its own constant speed, no matter what. This idea is more than just a quirky fact about light. It's one of the key principles of Einstein's special theory of relativity, which revolutionized our understanding of space, time, and motion. So next time you flip on a light switch, remember that you're observing a fundamental law of the universe in action. So, no matter how fast you're moving, light always travels at the same speed. This mind-bending idea is one of the cornerstones of Einstein's special theory of relativity. E equals mc squared. It's probably the most famous equation in the world, but what does it really mean? Imagine we're having a very special party, a cosmic party if you will. At this party, we have three guests, E, M, and c squared. Each one of them is a superstar in their own right, representing something fundamental about our universe. E stands for energy. Think about the last time you ran around the park, or when you're doing your chores really fast because you want to play video games. That's energy. Then we have M. M represents mass, which is a fancy way of saying stuff. The chair you're sitting on, the device you're watching this on, even the water in your body, all of that is mass. Finally, we have c squared. C represents the speed of light, a constant that's incredibly fast, so fast that it's almost impossible to comprehend. And when we square it, or multiply it by itself, it becomes an incredibly large number, making c squared a superstar in its own league. Now, back to our cosmic party. Our host, Albert Einstein, introduces these three guests to each other and says, "Guess what? You're all interchangeable." What he means is that energy and mass can be converted into each other. To understand this, let's imagine something you've probably seen before, an ice cube melting. When the ice cube is solid, it's like the mass in our equation, but as it melts and turns into water and then steam, it's like it's turning into energy. It's still the same stuff, but it's changing form. That's what Einstein's equation is telling us. Mass can be converted into energy and energy into mass. This might sound like crazy talk, but it's happening all around us. When the sun shines, it's converting its mass into energy, which travels to us as light and warmth. And it's not just the sun, it's happening in every star across the universe. And it's even happening right now, inside your own body. Yes, you heard it right. The food you eat gets converted into energy that fuels you to run, jump, and, of course, think about complex stuff like Einstein's equation. But what's truly mind-boggling is the c² part of the equation. Because the speed of light squared is such a big number, it means that a tiny bit of mass can be converted into a huge amount of energy. That's the principle behind nuclear power, and, unfortunately, nuclear weapons too. Einstein showed us that everything in the universe is just different forms of energy, even the solid stuff we can touch. Pretty cool, huh? If I told you that you could bend time and space, you'd probably think I'm crazy, right? But that's exactly what Einstein did with his theory of general relativity. Now let's take a step back. You might be thinking, wait, didn't we just talk about gravity as a force? And you'd be correct if we were discussing Newton's version of gravity. But Einstein brought a whole new perspective to the table. He proposed that gravity isn't a force at all. Instead, he described it as a curve in space-time caused by mass and energy. Let's break that down. When we say space-time, we're talking about our three-dimensional universe, plus time. Imagine it like a giant, invisible rubber sheet. This sheet is what we're moving through as we live our lives, and everything with mass or energy, from the smallest atom to the largest star, creates a dent in that sheet. Now, picture a bowling ball sitting on a trampoline. The weight of the ball creates a dip or a curve, right? That's exactly what happens when a massive object, like a planet or a star, exists in space-time. It creates a curve, a dent, in the fabric of space-time. But how does this relate to gravity? Well, think of a marble rolling around the edge of that dip created by the bowling ball on the trampoline. The marble will naturally roll towards the bowling ball, not because there's a mysterious force pulling it, but because the path it wants to take is curved towards the bowling ball. This, my friends, is Einstein's revolutionary idea. What we perceive as the force of gravity is actually just the natural movement of objects along the curves created in space-time by mass and energy. Einstein's idea completely transformed our understanding of the universe. It revealed that space and time are interconnected, and that the presence of mass and energy can warp both. This has led to some pretty wild predictions like black holes and time dilation, which have been proven true by numerous experiments and observations. To sum it up, gravity isn't a spooky force reaching out across the cosmos. Instead, it's the shape of space-time itself. It's the curvature created by mass and energy. So, when you drop something and it falls to the ground, it's not being pulled by the Earth. It's following the curve in space-time that the Earth creates. And there you have it, folks. Einstein's theory of general relativity, in a nutshell. It's complex, mind-boggling, and utterly fascinating. It's a testament to Einstein's genius that he could completely rethink the nature of gravity, and in doing so, reshape our understanding of the universe. So according to Einstein, when we feel gravity, we're actually feeling the curve of space and time. Talk about a mind twist. From the speed of light to the nature of gravity, Einstein's theories have shaped our understanding of the universe. Let's take a moment to reflect on the magnificent legacy of this extraordinary mind. Firstly, we delved into the constancy of the speed of light, a cornerstone of Einstein's special theory of relativity. It challenged the foundations of physics by asserting that light speed remains unaltered, regardless of the observer's motion. Then we explored the world-renowned equation, E = mc², which unveiled the profound relationship between energy and mass. This revolutionary concept has been instrumental in advancements like nuclear energy. Lastly, we ventured into the idea of space-time curvature, the crux of the general theory of relativity. It redefined our perception of gravity and paved the way for modern cosmology. These groundbreaking ideas have not only transformed our technological landscape, but also reshaped our scientific thought. So next time you look up at the stars, remember the man who dared to see the universe in a different light. Albert Einstein.